Hi everyone! Today we're going to continue to learn about earth sciences, and we are going to learn about earthquakes. Before we do, let's take a look at a model of the earth. Now we know the earth is round, and the earth is covered both with land and with water. If I were to take a look inside, our earth is not hollow. On the inside, we have different layers. On the very, very top, this outer layer is the crust. Below the crust, we have the mantle. The mantle is a lot warmer, making it not quite a solid, somewhere between a solid and a liquid. And below that, we have both the outer core and the inner core. And these are very, very, very hot layers, making the mantle kind of more like a liquid. Taking a closer look at the model of my earth, we have land and both water. And once we open it up, very top is the crust, below that is the mantle, the outer core, and the inner core. To get a better idea of what's going on, I'm going to recreate the mantle with this spray cheese. This is kind of what the mantle feels like. Not quite a solid and not quite a liquid. But the mantle is definitely not a solid. Now on top of the mantle, we have the crust. Now my crust sits on top of the mantle, and since the mantle is moving, then my crust is also moving. Now, a few different things could happen. The crust is broken up into pieces or plates. Now we have the crust that's sitting on top of the mantle. And as I told you, the mantle is always moving, which means that the crust can also move. On top of the crust is where we have the continents and the oceans. Now, one thing that could happen is that these pieces or plates of the crust could move away from each other. As they move away from each other, this layer here, this part of the mantle, cools down. As it cools down, it can regrow new crust. Now, another thing that could happen is that these plates could actually rub against each other. As they rub against each other, it is not a smooth ride, it is a bumpy ride. And as they move past each other, this is what we call an earthquake. Now we have seen what happens when plates move away from each other and when they rub against each other. But what happens when these plates actually move towards one another? Well, as they move towards one another, one plate goes under the other. And as this plate goes under, then this part that's below actually melts and it becomes a part of the mantle. We've seen what happens to the crust as they move away from each other, as they rub against each other, and as they moved towards one another. Now let's see what happens to continents as the crust moves towards one another. So I have here my continents that are laying on top of the plates. And I'm going to have my plates now move towards each other. And what do you see happening? As the plates move toward each other, what happened to my continents? What happened to the shape? Can you recognize what I've created? Can you guess what we have done here? Well, moving plates as they move toward each other, this is how we create mountains. Pretty cool, right? Your version now. Now it's time for you to make your own model of the Earth's layers. From your enrichment bag, you will take one Milky Way bar out, not meant to be eaten. Go ahead, unwrap it. And you can place it on paper plate or a paper napkin. Using a knife, we are going to just cut it down the middle. We'll take a closer look both at the top and the inside. Now the very, very top layer is the crust, like we had seen before. And if we look at a side view, this is the thinnest layer, and this is the solid layer. And just like my crust before, you saw it was broken into pieces or plates, and my chocolate layer has also broken into pieces or plates. Now we're gonna look at the inside, and we're gonna see this ooey gooey layer here. This is the mantle, would represent that. This is the layer that's not quite a solid or a liquid, but it is more like a liquid because it does move, it's soft. It's very hot here, so the rock inside is melting. As we go down, we'll see this is the outer core and the inner core, which is the hottest layer. Just like we saw before with my other model, how mountains are formed, you are going to do the same thing with this Milky Way bar. We're going to have the plates come together, push together, and we'll see what happens. And this is exactly what's happening inside the Earth when two plates come together. You're going to take your two pieces very carefully and push them together. Let's watch. I have my two pieces of chocolate, and let's see what happens when the two come together. Well, look at that. What did we just create here? Another mountain. I love using models to help me understand things that I'm not able to visit, things that are too far away to see, things that are too small to see, or things that are impossible to visit, like the Earth's core. We just modeled it though with my Milky Way bar here. Earthquakes create lots of turbulence, lots of movement, lots of shaking. And what we want to do is we want to create buildings and homes that are safe from earthquakes, buildings that are not going to crumble and buildings that are not going to collapse. Today, what we're going to do is an engineering project where we are going to both design and construct a building that's going to withstand an earthquake. For this lab, you will need 1 pack of Jell-O, mini marshmallows, a pie pan, toothpicks, hot water, cold water, a mixing bowl, and a mixing spoon or a fork. To make your earthquake table,
you will need 1 pack of Jell-O. You will need a pie pan. You will need a mixing bowl and a mixing utensil, 4 cups of ice cold water, and 4 cups of boiling water. Now, if you read the back of this Jell-O box, you will see that we are doubling the amount of water to make sure that our earthquake table is nice and wobbly. You start off by opening the packet and pouring all of the powder into the mixing bowl. And you start off by adding 2 cups of boiling hot water into the bowl. And using your spoon or fork, you will mix until all of the gelatin has dissolved. And then you can go ahead and add the next 2 cups of boiling water and continue to mix, making sure everything has completely dissolved. Now you can add your ice cold water, 2 cups at a time. Go ahead and pour in the ice cold water. You don't need to add any ice in there, just the water. Pour your water in, mix again, and pour your last 2 cups of ice cold water into the Jell-O and mix really well, making sure everything has completely dissolved. Once you are ready, you will pour the Jell-O mixture into your pie pan very carefully, making sure that it's about halfway full. You may have extra, but we don't need it. Now this pie pan will go into the fridge for about 4 hours or longer until you are ready to use it.
While we're waiting for our earthquake table, our Jell-O to set in the fridge, let me tell you the materials you will need for your earthquake safe buildings. You will need mini marshmallows, round ended toothpicks, and a plate to work on to keep your surface clean. And of course, very important, your planning sheet. Before you start designing, there are some rules that we need to follow. Your building must be at least 2 toothpick levels high, which would be like this. Your building must contain at least 1 triangle, and it must contain at least 1 square. Now, before you start putting things down on paper, think in your mind, what do I have to do? What do I want my structure to look like? I'm not going to limit the number of marshmallows or the number of toothpicks that you use for this lab. But please make sure that it does have to fit onto your earthquake table or your Jell-O table. It can't be too big that it doesn't fit on there. The size of this plate is a good size to keep your earthquake safe building limited to. Let's start planning. Here is my design. Let's see if I have fulfilled my criteria. Well, my design is at least 2 toothpicks high, a little bit higher, about 2.5 toothpicks high. I have both triangles and I have both squares in my building. The one other thing that I could do is label that this is a marshmallow and this is a toothpick. Now what I'm going to do is look at my design and start building. If at any point I see that my building does not work, well, that's okay. I can come here and fix whatever it is that I need to fix, change whatever it is I need to change, and then continue to build with my changed version. Let's start building. I have my toothpicks ready, my marshmallows ready, my workstation ready, and most importantly, my plan. I'm ready to start. Well, here is my final structure. I had to look at my design and I had to come back and change it a few times because things did not work as I planned, and that's okay. I made sure to modify my label. But let's look and see. Am I 2 toothpick levels high? Well, yes, I have 1, 2, actually 3 levels high. I was only going for 2.5, but I was able to get 3. I have triangles. I was supposed to have at least 1. And I do have squares. I was supposed to have at least 1. The one other thing that I did is, and you will be able to do that too, is I had to cut some of my toothpicks in half to reach. They were too long, and that should be fine. You can go ahead and do that. Now it's time to test. Here is my Jello or my earthquake table that's set, that's ready to go. It's extra wobbly. Remember, we used double the amount of water. Now it's time to test, and oh, am I nervous. I'm going to put my building on top of my Jello, and we're going to have an earthquake for about 30 seconds. So let's see if I'm safe. So far, so good. Let's make it a little bit harder. So let's look at my earthquake building. Did it pass the test? Yes. I had a lot of close calls. Some parts of the structure look great. Other parts don't look that great. If you look, there are parts where it looks like it's kind of tilting or bending. And then there are other parts like here where it looks so strong, looks great. Now as engineers, our job is to design and to build. And engineers in the real world, they are scientists who come up with solutions to problems that we have. Now engineers, they don't get it right the first time, the first 100 times. It takes them a long time. But each time they make a mistake, they learn something. And they discover something. They discover what not to do, and that's important. And that's why the design is so important. It's to go back and look at your design and see what worked and what didn't work, and take notes so that future engineers and future scientists can also learn from your mistakes. Now, engineers, we don't give up if something doesn't work. If your earthquake building didn't work the first time, well, that's okay. You go back and you redesign and make it better. Now, you have a couple of questions to answer, and then on the second sheet, you will redesign. You can make a better design. How can you make it better? Could I say that, oh, well, my building was safe from an earthquake, I'm done? No, I can make it bigger. I can make it better. I can make it stronger. I only had to withstand an earthquake for 30 seconds. What if I turn that into a minute? What if I've done that already and I say, oh no, it's perfect? Well, I've used a lot of marshmallows and a lot of toothpicks here. And in the real world, this would be materials used, and these cost money. Could I make my building cost less money? That's also an engineer's job. Let's take a closer look at the building and see what parts need some improvement. As we look at my building, we see there were areas where it was a little unstable. The other side as well looks a little wobbly. What do you notice about this? Was this wobbly? Was this part wobbly? Not at all. What is the difference between here and here? Did you figure it out? The shapes are different. The sides are squares and the front are all triangles. Well, what's the difference? Let's see. Here I have a square, and look at how flexible it is. Look at how much it moves. Do I want my building to be able to move this much? Now let's look at the triangle. It doesn't move at all. I can't bend at all. The triangle is so much more sturdy. Now, what if I have a square, but I want to turn my square into a triangle? I did that a bunch of times. Well, here, look at that. I turned a square into a triangle by adding a diagonal. Now I have two triangles inside of my square. And let's see. Can't move it anymore. It cannot stretch. It is very stable. Now, we did a lot today. We learned about the material of the earth, what's inside of the earth. We learned how earthquakes are created. Remember, rubbing of the plates together. And we had an engineering project where we had to design an earthquake-safe building. Go ahead, make your building. Can't wait to see what yours look like. Good luck.